Antoine-Laurent Lavoisier's 1775 treatise on the nature of the principle which combines with metals during calcination and increases their weight, represents a pivotal moment in the history of chemistry, marking a decisive shift from alchemy toward a quantitative, oxygen-centered understanding of combustion and calcination. This work, while relatively short, directly confronted prevailing phlogiston-based theories, ushering in what is often considered the chemical revolution. To fully appreciate its impact, we must examine the intellectual climate preceding it, the specifics of Lavoisier's experiments and arguments, the immediate and long-term consequences of his findings, and the critiques and modifications his ideas faced. Prior to Lavoisier, the dominant theory explaining combustion and calcination was the phlogiston theory, popularized by Georg Ernst Stahl in the late 17th and early 18th centuries. Phlogiston, conceived as a fire-like element, was believed to be released from combustible materials during burning. Metals, when calcinated, that is, heated in air until they formed a metallic ash or oxide, were thought to lose phlogiston, leaving behind the calx. One significant problem associated with the phlogiston theory involved explaining the increase in weight observed when metals were calcinated. Proponents of phlogiston sometimes proposed that phlogiston possessed negative weight, a rather ad hoc explanation developed to reconcile theory with observation. Alternatively, some supposed that the loss of phlogiston was counterbalanced by the absorption of particles of fire, a notion equally unsupported by direct evidence. Figures such as Joseph Black, with his work on fixed air, that is, carbon dioxide, demonstrated the importance of gases in chemical reactions. Henry Cavendish's isolation of inflammable air, that is, hydrogen, further complicated the understanding of gases and their roles in chemical processes. While they made crucial experimental contributions, Cavendish and Black remained largely within a phlogistic framework. Even Joseph Priestley, who would isolate oxygen, remained a lifelong devotee of the phlogiston theory, attributing his new gas to dephlogisticated air, particularly conducive to accepting phlogiston. Lavoisier's 1775 paper directly challenged these firmly established beliefs. His approach centered on meticulous quantitative experiments, a hallmark of his scientific methodology. Lavoisier carefully weighed the reactants and products in calcination reactions, most notably with tin and lead. He heated these metals in sealed vessels with a limited amount of air. Upon calcination, he observed an increase in the weight of the metal and a corresponding decrease in the weight of the air within the vessel. Furthermore, upon opening the vessel, air rushed in, demonstrating that some of the air had been consumed during the process. To understand the quantitative changes, consider an experiment with tin. Lavoisier began with a known mass of tin and a known volume of air in a sealed container. After heating, the tin transformed into its calx, an oxide of tin. Lavoisier meticulously determined the increase in mass of the tin calx. Simultaneously, he determined the decrease in the volume, or more precisely, the partial pressure of the air inside the container. He found a direct correlation between the increase in the metal's weight and the decrease in the air's volume. He concluded that a component of the air combined with the metal during calcination, explaining the observed weight increase. He further showed that the air consumed in this process was respirable, supporting his emerging ideas about its importance in both combustion and respiration. Lavoisier identified this active component of air as eminently respirable air, what we now know as oxygen. He proposed that during calcination, metals combine with oxygen, forming metallic oxides. This direct combination explained the increase in weight, eliminating the need for hypothetical elements like phlogiston possessing negative weight. He clearly argued that combustion and calcination were processes involving the combination of a substance with oxygen, rather than the loss of phlogiston. This concept, while straightforward in retrospect, represented a radical departure from the established paradigm. The quantitative precision of Lavoisier's experiments provided compelling evidence for his theory. The conservation of mass, rigorously demonstrated in his reactions, became a cornerstone of modern chemistry. His meticulous measurements enabled him to formulate balanced chemical equations, a practice essential to stoichiometric calculations. The immediate impact of Lavoisier's work was significant, though not universally accepted. Initially, many chemists, including Priestley, remained unconvinced, clinging to the phlogiston theory. The ingrained nature of the phlogistic explanation, coupled with the difficulty in abandoning a theory that seemed to explain many observations, hindered immediate acceptance. However, the clarity, consistency, and quantitative rigor of Lavoisier's arguments gradually won over many prominent scientists. His work served as a crucial foundation for the development of modern chemical nomenclature. Collaborating with Claude Louis Berthollet, Antoine-François de Fourcroy, and Guyton de Morveau, Lavoisier developed a systematic naming system for chemical compounds based on their elemental composition. This standardization greatly facilitated communication and collaboration within the scientific community. For instance, the metallic calxes, previously described with varied and often confusing names, were now systematically named as oxides of the corresponding metals, for example, oxide of tin, oxide of lead. The creation of a clear chemical language was vitally important to the advancement of chemical understanding. Lavoisier's oxygen theory also had profound implications for understanding respiration. He recognized the similarity between combustion and respiration, proposing that respiration was essentially a slow combustion process occurring within living organisms. He demonstrated that animals consumed oxygen and released carbon dioxide, analogous to the burning of charcoal. This insight connected chemistry and biology, paving the way for understanding metabolism at a chemical level. Lavoisier's experiments with Pierre-Simon Laplace, using an ice calorimeter to measure heat production during respiration, further solidified this connection. They showed that the amount of heat produced by a guinea pig was directly proportional to the amount of oxygen consumed, reinforcing the idea that respiration was a form of combustion. Over time, Lavoisier's work profoundly influenced the course of chemistry. His emphasis on quantitative measurements and the conservation of mass provided a solid foundation for stoichiometry and chemical analysis. His oxygen theory replaced the phlogiston theory, establishing a more accurate and consistent framework for understanding combustion, calcination, and respiration. His systematic nomenclature simplified chemical communication and facilitated the organization of chemical knowledge. Later scientists built upon Lavoisier's foundations, developing more sophisticated techniques for chemical analysis and synthesis. John Dalton's atomic theory, for example, relied heavily on the concept of elements combining in fixed proportions, a direct consequence of Lavoisier's work on conservation of mass and the definition of elements. Further development of thermodynamics and chemical kinetics relied on precise quantitative measurements and theoretical frameworks, fully in line with Lavoisier's approach. Despite its immense impact, Lavoisier's work did face critiques and revisions. Some contemporaries questioned the universality of the oxygen theory. Certain substances, such as hydrogen, did burn in air, but did not combine directly with oxygen in the same way as metals. It took time to fully integrate hydrogen into the oxygen framework, understanding that water was a product of hydrogen combustion. Furthermore, the initial understanding of oxidation states and the role of electrons in chemical bonding was rudimentary. While Lavoisier correctly identified oxygen as a key player, the mechanisms of chemical bonding remained unclear until the development of atomic theory and quantum mechanics. The discovery of new elements and the development of more sophisticated analytical techniques also led to refinements of Lavoisier's initial elemental table. While Lavoisier identified many of the known elements correctly, his list included some substances that were later shown to be compounds. The French Revolution, tragically, brought a premature end to Lavoisier's scientific career. His involvement in tax collection as a fermier gagnol made him a target of revolutionary fervour. Accusations of counter-revolutionary activities led to his arrest, trial, and execution in 1794. The famous quote attributed to Joseph Lagrange, "It took them only an instant to cut off that head, and 100 years may not produce another like it," encapsulates the profound loss the scientific community suffered. In conclusion, Antoine-Laurent Lavoisier's 1775 paper on the nature of the principle, which combines with metals during calcination and increases their weight, represents a fundamental turning point in the history of chemistry. His meticulously conducted experiments, combined with his clear and persuasive arguments, directly challenged the prevailing phlogiston theory and ushered in a new era of quantitative chemistry. His identification of oxygen as the active component in combustion and calcination, along with his work on chemical nomenclature and the connection between respiration and combustion, profoundly influenced the course of scientific discovery. While his work underwent later refinements, its foundational principles remain central to modern chemistry. Lavoisier's legacy extends far beyond his specific discoveries. His emphasis on quantitative rigor, precise measurement, and clear communication transformed scientific methodology, establishing chemistry as a truly modern science. His story serves as a reminder of the power of scientific inquiry and the importance of challenging established paradigms, even in the face of deeply entrenched beliefs. It is also a sobering reminder of the societal forces that can tragically cut short even the most brilliant of careers, leaving the world to ponder what further wonders could have been unveiled.